Hi all. In this video, you will learn about an introduction to circuit theory. Circuit theory is one of the most basic concepts that all electrical engineers around the world might have learned in their very first year of their university. So it's an introductory course to electrical engineering. All the electrical phenomena happening around us is due to the charge Q. So before we proceed with the circuit theory and different types of elements, etc., we need to talk about the properties of charge. So here are the three properties of charge. First is charge is bipolar. That means charge can exist as both a positive and a negative quantity. Next is charge is discrete, which means that they are independent individual units. You can consider charge as independent individual units. Then comes the electrical effect. So all the electrical phenomena that we can observe in our surrounding is due to two things that happen to charge. Firstly, the separation of charge. Secondly, the motion of charge. Separation of charge leads to the formation of voltage, and motion of charge leads to the formation of current. So how exactly does this happen? When Q1 and let's say Q2 are separated from each other over a small distance d, we know that it's a universal fact that there exists an electrostatic force between these two. The potential of each of these charges to resist the force and stay in this position marked to itself is called as voltage. So voltage is the potential of each of these charges to stay in position and to resist this force that can bring these two closer to each other or bring these two far away from each other. So we can write voltage as dW by dq. Here dW is the amount of energy, the amount of energy required by these two charges to stay in position or in order to resist the electrical force that can bring them closer to each other or take them farther away from each other. Hence, this is a very important formula that we need to keep in mind. Next comes the motion of charge. So let's say this charge Q moves with respect to time. This motion of charge or this rate of motion of charge is what leads to what we call as the current. So current can be expressed as dq by dt. So these two are very important formulas, and of the most basic formulas that we need to keep in mind for solving a lot of problems. Moving on. A basic electrical circuit or any electrical circuit has what is called as elements, circuit elements. So anything apart from wires, anything that we find in an electrical circuit can be called as a basic electrical circuit element. So all these elements have the following three properties. Firstly, they have two terminals. Consider this box to be a circuit element. So this is a circuit element. Now this circuit element will have two terminals. This is terminal 1 and this is terminal 2. Secondly, voltage and current is defined for this element exclusively. So across this terminal, we define what is called as a terminal voltage, which is the voltage across the terminals, voltage in between the terminals of this particular element. And with a small arrow, we show the direction of current. So this is the current that passes between the terminals of this particular circuit element. Third property is it is basic. That is, this is the basic unit of any electrical circuit. This cannot be broken down into further subparts. That's not possible. So this is a basic element. These are the three properties. So an element can be anything that we might have come across in basic courses. So it can be a resistor, it can be a capacitor, or it can be an inductor. As you can see, these are the elements. They have two terminals. Each of these have two terminals, and the terminal voltages for each of these elements can be defined, and the amount of current passing through each of these elements can also be defined. And it's one of the most basic. There is no such thing as a sub-resistor or stuff like that. This is the basic unit. This resistor cannot be broken down into smaller units. So that's the basic element. Moving on. When we design an electrical circuit, the outcome or the output of an electrical circuit is always something non-electrical. So it can be either in the form of heat. We design a circuit for heat or sound or light. So it's always something non-electrical, right? Therefore, in order to define or in order to think about the application of electrical circuit, it becomes very important to define power and energy in addition to voltage and current, because this alone is not sufficient. All right. So we define power as the rate of consumption or expenditure of energy by the amount of consumption or expansion of energy by the circuit elements. So we can write power as dW by dt. It's a rate of expenditure or consumption of energy by the circuit element. Now, this formula, keeping in mind the basic mathematical laws, can be rewritten as dW by dQ into dQ by dt. And as you have seen from previous explanations, that dW by dQ is nothing but our voltage and dQ by dt is nothing but our current. So power can be rewritten as VI. This is a very important formula again. This is very much useful when we deal with problems in future. Now that we have defined power, current and voltage and discuss about the properties of charge, it becomes very necessary to understand the sign conventions used in electrical circuit, but because this can be one of the most mind-boggling things. It can be one of the most it can be one of the areas where frequent errors can happen. So passive sign convention is one of the most easiest sign convention. It's very simple to understand too. The idea is simple. Consider this to be an electrical element. It has positive and negative terminals, and then it has some current I passing through it. If the direction of current is same as the direction of voltage drop, then we can assume positive sign. As you can see here, the voltage is dropping in this direction and the current is also in the same direction. Therefore, we can assume a positive sign for this element for power calculation, etc. If the direction of current is not the same as the direction of voltage drop, then we can assume a negative sign. So an example for this would be so as you can see, the voltage drop is across this direction, but the current is flowing in the opposite direction. Therefore, we can assume a negative sign for power calculations, etc. As we have discussed earlier, power can be written as VI. So in the case of the first circuit, let's mark this first and second. So in the case of the first circuit, we can see that the current is in the direction of the voltage drop. Therefore, we can write plus VI. So the power will be a positive value. In the case of the second circuit, both the voltage drop and current are in the opposite directions. Therefore, we can write minus VI. So the power in this case will be negative. If the power is a positive quantity, it means that the element, this particular element, is consuming energy. It is consuming energy. That means the power is given to the element. However, if power is negative, then we can say that it is giving out energy. The element here, it is giving out energy. That is, the power is being generated by this particular element. So these two are very important concepts. Now we need to make certain assumptions before we proceed further with circuit theory. First is electrical effects happen instantaneously throughout the system. Now, some of you might have learned that electrical energy can travel in the form of a wave, and it means that there exists some kind of unevenness in charge distribution or the energy carrying capacity of different parts of one single wire and things like that. But if you consider this case where the wavelength of this particular wave, electrical wave, is much larger than the size of the electrical circuit that we are dealing with, in that case, we can say that electrical effects are uniform and it can happen throughout the system in a uniform manner. So what is this size of the element? And in real life, does the electrical circuit apply to this rule? Well, that's actually true, because if we consider this electrical wave is traveling at a rate or at a speed of c, that is the speed of light, then through all these mathematical calculations, we can assume that if the size of an electrical circuit is less than or equal to 5 into 10 to the power of 5 meters, then we can call it as a circuit which is where the circuit theory can be applied. The different concepts of circuit theory can safely be applied. And in real life, all the circuits that we're dealing with is surely smaller than this size. Therefore, we can safely apply circuit theory concepts to any circuit around us. Next is the net charge on every component in the system is always 0. Even if you're confused about capacitors, a capacitor is always, having a positive and a negative charge, like, a positive and a negative charge, and together as a system, the net charge is always 0. Therefore, this doubt can also be ruled out. In the next video onwards, we'll dive deeper into this subject. Thanks for watching.